Boy, of course. Do you stay in the exam? Yeah?
Yeah.
On the way back, I just saw a big deer.
Really?
Jumping 5 meters from me, yeah.
Oh, that's cool.
Yeah.
Have you seen board?
Boars.
Yeah.
Yesterday we went with Université very late. Bit dark. We heard something, but no, not really. Yeah, my student here.
I keep it open and just in case someone doesn't find it.
Is it registered? No, is it registering? Ah, okay, it's not recording. So we can start.
We can start.
Yes.
Finally, we can start. Everything is fine. It's recording.
Yeah, let's start our morning session. The only talk is by Jennifer Brown, and she will tell us about categorical approach to non-semisimple scale. Please.
Yeah. Thank you. Thank you for organizing and for sticking around. And thanks for everyone for coming. So today I want to talk about a recent project that I had joint with Benjamin ıoun. And what I want to do is I want to first start off by talking about what is this categorical Skein theory stuff. After that, I'll talk a little bit about what goes wrong when we have some input category and it's non-semisimple. And then the sort of third part of the talk is how do we reconcile these two approaches, which for a long time were sort of incompatible. Okay, and feel free to ask questions, of course. So let's start off with this categorical Skein theory. What's going on here? Just briefly, I know we have experts in the room. The way I like to think about this is given a ribbon category A, and just to recall ribbon category, this means that this has some grading. It's rigid, and it's pivotal. And there's some compatibility between all these structures. Pivotal, of course, means that we have some non-dual identification between left and right duals. So given such a thing, I can construct a few nice things. I can construct a functor from some category of surfaces, which has objects as oriented surfaces. So that's the objects. The morphisms are going to be embeddings, also oriented, and then my two morphisms are isomorphisms of those. So I get some functor from here to the category of k-linear categories. So this has k-linear categories. One is going to be k-linear functors, and then two morphisms are natural transformations. So I can construct some functor like that. Let me give it a name. Let me use all the colors I tracked down this morning. So this thing I'll call Skein cat. It depends on this, so I'll call it Skein cat like this. So I can construct this. I can construct also a categorified 3D TFT. And what does this mean? It means something from a category of cuboidisms with surfaces in 3 manifolds into some other category, and here is some category by mod, which has the same objects here, but the functors are a bit different. And this is about as low as I can draw, right?
You can.
I can draw like one hand span lower. Okay, so I'll use that extra hand span to say that here are the one morphisms. They are profunctors. So what this means is something that goes from, instead of C to D, it goes from C to the functors. Be like this. So I can construct those things. And I have a theorem to write here because extending this theorem was the main part of the project. So the original version of the theorem is in Juliet Cook's thesis from 2019. So this is sort of some semi-simple setting. And then the work 24 was to extend this to non-semi-simple, which is that if I take this functor at A, this is the same as doing factorisation homology. You know what that is?
What it is?
Hmm?
What it is?
What it is?
Anal experts. This.
Yeah. So factorisation homology, what it is a way to take a functor from some category disk, which is a subcategory here of SIRP. I will let you guess. It's where the objects are disks.
So surfaces are closed or open in your first line?
Yeah, they can be open. They can have
It
boundaries.
can be open, okay.
Yeah. And here I have some category from disk, some functor from disk to cat. Factorization homology is more general than this, but this is what we need. So here I have some functor. And if I want to extend this, here, factorization homology is just some way of extending that functor. It's defined using a colimit, but that's what it is.
So what is that? Just so any function?
Some functor.
Any, you don't ask it to be monoid or something.
Yeah, so it ends up being, yeah, we'll want it to be monoidal.
And symmetric?
Yeah.
So we can only have such a link for a fullback or
You can't. You remember the conditions when you need it?
It depends a little bit on how you define this, but it is a monoidal category with several.
Yeah.
It could be symmetric monoidal, and factorization homology is the Khan extension.
Yeah. Okay. So this is the
So
second.
Skein path is also a symmetric monoidal function, right?
Yes. Under a disjoint union. Sending it to.
And then what is categorical TFT?
The what?
I mean, the second one, I didn't get it.
Oh, this is so I'll give you maybe 30 seconds of discussion about this because it's cool.
But here surfaces are closed, objects in a cobordism category, it's usual cobordism category, right?
Yes. Yeah, so it's the usual cobordism category because of this. One of the sort of, you can see it as defining properties of factorization homology is it satisfies some nice excision. So I was going to talk about this. So here's some properties that we get. So one thing, which will be relevant to your question of it, is that we have excision. Meaning if I have some surface glued together on two smaller surfaces, so some cartoon like this, then I get at the whole thing on sigma. All of it from the Skein category, whatever coefficients of all the sigma. I can build this as a one. And this is some relative tensor product over Skein category of this sort of thickened. So because of this property, you can actually extend this down, but yeah. Okay.
But in cobordism to 3, surfaces are closed.
Yeah, you do it with closed. Yeah.
And what is the target?
But the target is bimod.
What does it mean?
So this is something you have. I'll start giving you some facts about this. So this is something you can take cat, you can enlarge it to bimod. It has the same 0 morphisms, same 2 morphisms.
Oh.
1 morphisms are different. There are these propuncture things.
So good question. These scaling categories, do they have to have anything else? Any completion on the sounds? Just any.
No, but we do often in this domain like pass to the free code completion. So sometimes you need some completion properties, but you will just work in the completion. This is very necessary.
So instead of being functions between C and D, your morphisms are functors from C to
like
functors
here,
from the opposite to functor category?
yeah. So here it's it would just be a nice functor with C to D. And here it would be something like this.
Oh, okay.
Yeah.
Just in your
Against,
categories, you don't ask them to be a alien or anything.
No.
Just in your alien.
I need them to be.
Okay.
For some tools, you want them to be linear, but this part we want them to be linear, and it's small.
But will you give us example, say of Skein cat or something, because
I was gonna.
people are not expert here. It's good
Yeah, I
examples
can
and
give you an example. So here are some examples. If I take my ribbon category and I just take it to be Repq G, which is some reductive group, this is symmetric monoidal, that's also graded. Then the Skein category, Repq G, and the surface is the category of positive coherent sheaves on the G character stack. So like that, which I guess in particular means that if I pick the Skein Repq G Skein category of just a disk, I will get I'll get Repq G back.
So how this function is defined? Is like geometrically or?
Yeah, this will be the next part. So
Okay.
yeah.
So it's like G, at least.
Yeah, so this one will be Repq
So
G.
this cat.
But now you did already co-completed that.
Yeah. Yeah, I'm gonna be sloppy about what I put.
Okay, fine.
So let's talk a little bit more about Skein categories. I would say philosophically, when we work with them, or at least when I work with them, I usually use their properties as opposed to like writing them down concretely. So these become very important. So this property comes from this relationship to factorisation homology. Proving this is actually how this was originally proven. Another one is that it's the Skein category is going to be monoidal when sigma is some significant curve. So this happens a lot in math, but if you have some extra structure, topologically it relates to some extra. And this is just from the fact that if I have two thickened curves, copies in my thickened curve.
I see the curve on
Yeah.
any surface, right?
It's just like a topological curve. I mean,
Oh, okay.
C is a bunch of circles in intervals. But when I have such a thing, I can embed it into itself. Just kind of a special property of surfaces. Usually I can't embed two tori into another tori. Right? So this together with this functoriality produces some monoidal structure on the Skein category, but otherwise I won't have one. It's also a nice kind of technical point, but it turns out to be very useful when I'm
Strict by construction. The function is Skein function is strict.
I would have to think about that. I mean, here you have like a bunch of isotopies.
No, I mean, but you have to say what is associated, right? But okay, yeah.
Oh, yeah,
Associated.
I would have to think about it. And then the last thing that I want to bring up, because it shows up sometimes because it breaks down in this non-simple setting, is it's also pointed. So I allow the empty surface here, and this embeds uniquely into any surface, which means that I have some distinguished object inside my Skein category always. And this distinguished object is we like to use it in constructions. So now this is a lot of nice properties. Let's say what the Skein categories actually are. And to get to Skein categories, I'll give some other definitions. So when we're starting off trying to do Skein stuff, which by the way, I'm on a mission to mention in every seminar, Skein is not someone's last name. It looks a lot like a German name, but Skein is like the English word for like a bunch of yarn. So this is what Skein is referring to, is like a bunch of yarn. But when we're doing Skein theory, we need to have Skein relations. And these What they come from is something called the evaluation functor. We'll often call it the derived evaluation functor. And this is a functor from a diagrammatic category. I'll say what it is. That's the original category. Which really makes precise this sort of graphical calculus. So let me change colors because I'm doing that in a while. So this is going to be a category whose morphisms are going to be embedded graphs. So there'll be subgraph. So maybe I have some graph embedded like this. They're going to be embedded graphs. What I want is for each edge of the graph to be labeled by some object of my category. I want all the edges to be oriented. And I want at each vertex, I want to have some morphism in my category. Yeah, these things. So I'm going to just write out all of these things. These are going to be A labeled. People also colored sometimes A labeled framed oriented graphs. And some like this. And then the objects are just going to be the top and bottom. So an object is going to be a disk with also frames. I'll just say signed. A labeled. Okay. And you can decide your convention if it goes up or down. So this is this. And what we want with this functor is doing is it's taking one of these graphs and really relating it to some morphism. So this functor would send us to some phi from V to W. There was some duals depending on the orientation. Okay, so this is this functor. There's a important thing about this functor from which you can derive in the 90s is that this is RTA is determined by two things, by being ribbon. So this turns out to be a ribbon category. So it has some braiding, it has to be sent to the braiding, it has some product, it has to be sent to the product, and so on and so on. So it's being ribbon, and also that RT of, I'll change how I'm drawing things a little bit. So what I'm going to do is take these vertices, draw them as boxes, right? Space to write something inside of them. It has to send such a vertex to the underlying morphism, and it has to send something labeled V plus V, and then also space here goes minus V. So we have to be set to V. Okay. So it's such an evaluation functor. And what does this evaluation functor give us? It gives us some relation on morphisms here. So this is k-linear and with this 3k linear, so I actually allow for sort of sums of such things. So maybe I'll place 0 thing here. And what this gives for us is Skein relations. Also, on a scale of 1 to 5, how awful is it to read when I like half erased like this? Middle 8 awful, not that bad. Okay. So again, Skein relations. So these will be between morphisms in this category of graphs. So whatever these are, some labelings. So these two will be equivalent when RT A gamma. Right, A. So this gives us our relations, and I'll just. The fact that I basically, you'll see it has come up in some guys in the board already, is if I take Rep A, and then I quotient out these vector spaces, the Hom spaces by this relation, what I'm gonna get back is just a model for A. Right? Okay. Let me, before I embark on the racing stuff, let me write some examples. So when you saw Skein in the title, you may have expected me to just write this on the board as sort of my first line. This is often the first thing we write. And this shows up in this setting when in this formalism when this is Repq SL2. And here how what's going on with the orientations, it's all oriented like this, like this. This one you may realize there's no good orientation. There's some coupon that lets us change the orientation like that. So that's how that shows up. But the point I want to make is most of the Skein relations you'll get here are just boring, sort of bookkeeping stuff. But there are a few that are interesting with that. Okay. Let me. So here. It's the difficulty racing has a good impact.
No, so.
Like,
Huh?
we all get a moment to
We have
like.
all a theory about black box. Yes, before powder.
We have to use this geometry.
No, she
I
had good comments.
Say again? I was considering trying to find like a bucket of water this morning. In my experience, if you try the German system outside of
Yeah.
Germany, it goes horribly.
I thought that you didn't agree with the water cleaning.
So here's the thing is if you clean it wet and try to clean it dry, you're just like it doesn't work. But you have to stay. Yeah, it takes a lot of water in it. I mean.
Or a lot of water or no water.
From the experts.
Okay.
Okay. So let me write some stuff that I erased. So there's this that we like. We also I want to recall that there's this point here, which is important. This will just come up if we talk about non-semisimple stuff. So now I can some more. So I think
And the monoidal structure in K is just Cartesian product,
yeah, I mean it's
right? It's
called like the Lane tensor product.
say it?
It's like the Lane, yeah, it looks a lot.
No, they need kind of take Berlin, right? That is yeah.
Oh yeah,
What
there's
I mean by Berlin.
yeah, okay, yeah.
That's why I was asking if they whether they are a billion or not.
There's the link on this. Technical things. Okay. So let's continue on this quest to define the Skein category I was bragging about earlier. So here's the definition. The next definition. In this category of A, I had these objects which are labeled disk. I just want to put up the name for generalizing this. So I'll call it A labeling. Most of this is, so this is just going to be a finite collection of framed signed this A labels. What's in sigma? Not that interesting, but I find if I ever try to skip defining it during a talk, it causes massive confusion. So it's just something like this. You understand why this is plus minus, something like this. So here's what an A labeling is. And now the thing I want to do with these is I want to build the relative scheme module. So what this is going to be, I'll write in SK sub A because it is my root category. It's going to be something for a 3-manifold M. And for, if I use X, this is going to be a labeling of the boundary of M. Okay, so this is going to be the span of A labeled ribbon graph in M, such that, so such a thing, maybe I'll call such a thing gamma again, such that when gamma, I of course restrict it to the boundary of X. And then this will be up to the same thing, and I'll do some local Skein relations. And what are these local Skein relations? So here's my picture. I have some surface, and my 3-manifold, and I'm looking at graphs embedded here. They can have coupons, they can sort of interact with themselves like this, and it's all framed and oriented and labeled like so. So this is such a gamma. And when I defined my Skein relations, I defined them in this category of A. So what I need to do in order to make sense of that is I need to embed cylinders such that when I restrict my graph to my cylinder, I get something comprehensible as normalizing. So if I take this cylinder, now I can see this is I get something in morphism A, so I can define some relation here. So I do that for any cylinder I embed. I can have these Skein relations. So you're starting to see.
It should be inside a 3-ball or.
Yeah, it's like a thickened cylinder. So it's like it's a 3-ball, but I want to care about going off to the top and the bottom. So I put some extra data on the boundary. But people like Kevin Walker, if you know this name, he like often just use embedded spheres. So, or sorry, embedded balls. So both happen. I will say, because there have been questions about computations, unless you have some extra tricks, this is going to be a nightmare to compute, right? Because it's generated by like all embeddings of graphs up to isotopy. I didn't say it, but then you also have an insane number of relations. So this is, you need some special tools to compute this. Okay. So I've done all this so that I can define my Skein category. Skein category A, the sigma, linear category with objects are going to be A labelings with sigma, and then my morphisms. Well, I'll just think what the Hom spaces are. So the Hom spaces between X and Y to these labelings. This is going to be the relative Skein module. of the thickened surface. Or I put X on one boundary and Y on the other boundary. Okay, so this is what we have. The pictures that you would think of is, if I have some annulus here, then my morphism spaces look like this vector spaces of embedded graphs. So this is an example of a morphism in this category.
Like object item labeling of signals. Okay.
Yeah,
Okay, category where objects are surfaces with labels.
so the surface is fixed.
Surface fixed, yes.
Yeah, the objects are the labelings. It's like, are like the.
All the many object, sorry.
Yeah, so I take my surface, it's fixed here, and then I can put some
I think
finding.
of them auto isotopy or something, like.
No, but isotopies will give you isomorphisms in the.
Isomorphisms, okay,
Yeah.
but you don't.
Yeah.
So you have crazy amount of objects.
Yeah, it's a crazy category. That's why we need tools like.
But you have many isomorphisms.
vision and stuff like this, like if
But you have many
you.
isomorphisms, yeah.
Yeah, it's very many, you have a lot of isomorphisms. Okay. Now, so that I'm not tempted to go over time, I'll just do some research intermission. Just to say what I'm doing with this, so that it's not at the end and I don't rush to be able to say these things. So a major goal I have is to study, and that isn't often being quantized, instructions on character varieties and stats using the Skein theory. So, sort of an example, which is just a first paper on it came out this spring with David Jordan. Is understanding, if you know what it is, there's some not invariant called the A polynomial. That you can build using these character stacks, and we give some quantization of it. Design that has been sought for a while, and we give a new way of quantizing it using this technology. And the main tool there, which I'm not discussing slides right now in this talk, is introducing defects. So allowing us to work with some setting where, say, I'm looking at the Skein category of the disk, but in different regions, I want different variant categories. So I have like maybe A here, A1 here, A2 here, A3 here. So some situation. And there the like actual the main example, which is the most motivated, is where this is Repq G, and it's then construct the maximum source, so maximum course in G, and then where my defect is determined by some parabolic umbrella. So that's the sort of thing that we're doing. And
Defects are not bimodal categories over these two, or what are they?
yeah. I mean, they should be bimodules for this. I mean, they should be like the data will have some defect between A1 and A2 could be starting from A1. And so the gradient opposite to the dental center of the defect. So the bimorphisms way. So that's the thing, and then how it fits into this talk is some longer term goal to extend this sort of geometric theory to non-semisimple settings, especially these super objects. Okay, but now we can get cut off at the end, but I won't worry about having not mentioned my research. Instead, what I want to do is talk about what goes wrong. in this theory when this category is non-semisimple. Of course, I can run through these definitions, make sense of them when it's non-semisimple. But I can get some sort of unfortunate behavior. Okay. What goes wrong? Let's just do a little computation. Let's say, let's go like this. If I take some closed Skein and I color it by a projective like this is some projective in A. If this is equivalent to the empty Skein, there's no Skein anymore, times some C is non-zero. So if I can take this, use my Skein relations, get rid of it, then the unit in A is projective. Right?
Yeah, that's fine.
And this is possible.
Then S is simple.
Yeah, so this is projective. And then the last part is this is semi-simple. And how does this fact go? Well, what you do is we take this thing and you notice here, if I look at the bottom half, this is some morphism from the unit to P tensor dual. This is also projective, and then I have a map back to the unit. So if I take one of these and I multiply by 1 over C, then this whole thing is a retract. So I can build a retract of tensor P dual. And so a retract of a projective is projective. Okay. So what does this imply that I guess the contrapositive is that if A is non-semi-simple, then if I take this is going to be equal to 0. This will be any closed loop by projective. More stuff than this will be 0, but this already is so Pascal doesn't show. And what this means is our theory sort of collapses. I didn't discuss it during this talk, but for instance, one thing this means is I can't make meaningful non-invariants unless I do something special. And what's the solution? Which is a really long theorem that's already come, or a long program that's come up a few times during this conference series. So the solution that people have been looking for a long time now is to impose admissibility conditions. What does this mean? what we do is G, we only consider reductive labels. What does this mean? Well, I take my category, this whole thing, group A, that I was considering before, and I look at the full subcategory. Where I have to color. So then I only color my reductives at on the objects. And I can just restrict my evaluations onto T. I can restrict it here. And I will end in blockchain. Like this. So this is the solution. This is the only my favorite example of a CP driven category, which came up yesterday. Why does this help? Well, this helps because let's just look at how this thing falls apart. So here, when I'm making my Skein relations, I need to understand this whole thing is some morphism in my category of ribbon graphs. And this closed loop is a morphism here. But not here because it's a morphism from the unit to the unit, which is not really there. So I could do some, so I just don't have some Skein relation here. So I can put some Skein relation on this part, but I can't get down to here or up to here. So it sort of stops me from getting rid of these loops.
So you don't have closed graphs.
Yeah, I won't have closed graphs.
You will not have closed graphs.
Yeah, I won't have closed graphs. So just
You will not have empty surfaces.
yeah, so I will not have pointing anymore. Yeah. So but let me just put that on the board. Here, this projective P is not related to anything. Times the empty. So it's not related to that. Right, because this is not something I can agree with. Okay. So this is the solution. Let me just write some, I mean, I won't write all the names I should, because this has been a big group project, but some people have worked a lot on this. Listen to that. I always forget how to spell the last part of the name. So like this. Something like this, right? Okay, so this is like so, and what this causes problems for this categorical approach, which is now I have no empty object. Right, because the unit isn't, yeah, I have to have some projective version here. And what that means is that implies this Skein kind of A isn't defined on this empty embedding. Like this, because this would be sent to the empty object. And this causes problems. We will use this empty object in many constructions. So for instance, we like to look at in the morphisms of the empty object. This is called the Skein algebra. We like to look at internal endomorphisms of that. This is called the internal Skein algebra, and so on. And now we can't play any of these games because we don't have that object. And so in my last 5 minutes, what I wanna do is talk about how do you get around this problem.
What was last time? We used
Oh, we just-
many construction.
Yeah, mini constructions.
So what is this equality? Again?
This is a definition. So I'll do this one first.
Yeah.
But if I just look at endomorphisms of the empty object, this will look like my surface. Like through an annulus. With, curves, goes graphs in here, and then the endomorphism algebra will be like stacking. How's that? So I get some algebra, and this is like one of the main things that we study.
Oh, Skein algebras.
Yeah, Skein algebras. So we would like to have it, Skein theorists would really like to have this empty object. Okay, so what is the workaround that we do? Is we work with bimod. Instead of cat. Yes. So what does this? What does this mean? So we already discussed some of the differences here, but just to recall, this is the main difference is that here I just need a little bit of find something like this. And what will come out of this is that in this version of it, this is as functors from strength bimod. In that version, whereas in the original version, it was the cat. So what is this? How does this help? Well, the main idea behind how this helps is we need a projective labeling in each connected component of M, whatever free manifold we're dealing with, not its boundary, like this. And why do we need that? So let's think about this. So if this had some other boundary component here, so if this thing here, one of my relative Skein module, had no projectives anywhere in it, then it would not be related to anything in this Skein category where I want my projective objects, right? Like there would just be no relation between it. But as long as there's
So you don't allow such skeins. You don't allow such skeins, right?
yeah, I don't allow such skeins, so it wouldn't be, it's not gonna be related. So you could
Right.
say, well, maybe you could just allow the empty skein. Jenny, calm down. But then the empty skein won't be related to anything else. So I'll have my theory and then I'll have this empty skein that's just completely decoupled from the rest of it. But as long as I have a projective somewhere in my 3 dimensions, I'm fine with it. I relate to the rest of the theory. And it doesn't need to touch every boundary component for it to be related. But this is the key thing is it's really important to have projectives in every 3-dimensional component, but not in every boundary component. So what this means is that if I
The
have,
boundary can be empty, right? Or
yeah, so the whole boundary can't be empty.
cannot be.
Yeah, the
Cannot.
whole boundary, I don't want it to be empty, especially in this thing.
Yes, yes.
But I mean, if one component is empty, that would be fine,
Mhm.
right? So what we can do that means is I can say this functor,
Sorry, but labels on the boundary, they don't need to be projectives.
they do.
They also need, okay.
Yeah.
But then you will have necessarily an edge inside M3, which is projected.
Yeah.
Okay.
So this is why I only need it in, as long as there's a projective label in some boundary component,
Okay, in each
connected component
Okay.
of the three manifold, then that component of the three manifold
Yes,
will have to have a projective. Um. So this is what's going on, and what this means is that if I take my relative Skein module functor, I have this component. You go 0, 1. And here, what I will do is I will put maybe nothing on. No, that's too up. That's too up. So nothing on, say, the 0th. And then here I have my space, and this part here is on the other boundary component. This thing is going to give me a functor from Skein category of the empty surface in my Skein category, whatever surface I want. Just because it doesn't matter that on one of them I put nothing, because the other one on, because I yeah, because the other one I can't put it directly.
So the left-hand side is just, it's a Skein module, what we call Skein module, right?
Yeah.
You have a 3, and then the boundary.
Yeah.
Sigma 0, sigma 1.
Yeah, okay, let me think. This
So
is actually,
the red boundary, it's a sigma and sigma reversed orientation.
yeah, because I want, I've done it,
Yeah, it's a cylinder, and then you.
yeah, but just. So this is my X, so I would have any, I think I actually confused the convention of when. So something like this would be in here. I'll switch. Okay. So actually. Sorry. I'm rushing, I wrote this wrong. So here I want something here. Up, because the orientation reversing. These goes to that. So this whole thing here, this will be the image of the this inclusion will get sent to this thing. So the takeaway is that I have no empty object, but I have something this is notation people use sometimes, but I have a functor that would be represented by the empty object if I had the empty object. So I have some analog that's pretty close. And so what that means is that when I need this pointing to use this theory, then I have something for this bedding to land on. And also I have some analog of the sort of the distinguished pre-sheet that I can use in sort of these constructions here. So here I could write some hat here. And this would be my Skein algebra in this setting. And if it's if I did have some admissibility condition, if everything was projective, then I would just recover Skein algebra. But I think
So this is
that's 1101.
this is the new one, which is with target by mode. Is it?
Yeah. So this is the new one for your diagram. But I think we should clap. And then
But if you want, it's for 5 minutes.
no, this is the natural place to end.
Okay.
Yeah.
Thank you.
So then,
Other questions?
Is there something that speaks against reversing the orientation? The last thing you can do.
Oh.
Switching the blank is the empty.
yeah, so it was this came up between maybe in a too quick and quiet conversation between me and Zach, that you want to reverse the orientation because you want this to be contravariant.
Oh.
Yeah.
Any other questions, comments?
I have another comment I should say, independent of our work and equivalent time, Rinkel and Steiger also had the same result. So they also did work on this. Sort of,
With whom?
Tom.
Okay.
okay, thank you.
No.
So also that like these admissibility conditions don't mess up excision properties.
So I question, these three nice gentlemen you mentioned, they usually go around this problem using modified traces. How does it? I mean, first, why do you want to use modified trace, or you want somehow
Yeah,
to recover modified trace, or?
Yeah, I mean, so they have a big focus on modified traces. My understanding is because they're just trying to use this theory to do something a bit different than I am.
So
They're using it to make like not invariance into steady
yeah, of
case.
course, yes.
And that's just like a little bit orthogonal to what we're doing, but it is
Is it a little what?
orthogonal to what we're, I mean, we're not using this to make not invariance, I'm using it to,
Yeah, right, we have Skein theory, or maybe you say,
Yeah.
like go around it, but
yeah, but it is a.
would it be helpful for you, or like, because then you could still use empty object, right?
Yeah, I mean,
You could say you use a Skein derived, I mean, you can extend a Skein derived function.
what they're doing is they're yeah, like getting around the fact that they're like allowing you to build a not invariant by like opening up the not.
Yeah, like
Right.
Skein derived, it would be modified Skein derived, like that
Yeah,
group
yeah,
will be evaluated to something which is not zero.
Yeah.
Yeah.
Yeah, I would say, I mean, it's not like,
When you don't have to put it in, but it comes
it's
out,
there.
right?
Yeah,
So when you evaluate these Skein modules, for instance, on S3, then Cosentino, Gephardt, they show that for S3, you get the space of modified traces. So then you choose
Yeah.
one, and then this allows you to turn some things into a number, but you don't put this into the construction. It comes out actually. You can show that this leads to modified traces.
Yeah, but data structure is slightly different, no? Or, I mean,
So,
I'm talking about your construction.
yeah, so yes, this is, thank you, I was.
Yeah, but they don't put modified traces.
No, I understand, but my question is how modified trace related to your construction, or how does it appear? Can I say?
I also think for us, it would be like. Yeah, like you plug this here, you look at like the 3-ball and you wanna pick some isomorphism with the ground field, and this is like your modified trace thing. It's, so the place where our construction starts to deviate from theirs is that they have a alternative definition of what you should do with the Skein algebra when you have admissibility conditions.
Mhm.
And these things are, we say, not quite the same algebras that you get, but I mean, us and them know we haven't worked through the exact relation. Yeah, so that's where they differ, but I think you get the modified traces coming out of it. Yeah, I mean, our main focus is that we wanted this factorization homology.
Why projective ideal is so important? Like, why don't you another kinds of ideas?
Yeah, so that was a bit of a narrative choice for this talk. A narrative choice for this talk, to just focus on the projective ideal.
I see, yeah.
But it's, you can pick any ideal, but it's always gonna contain the projective ideal.
Of course, but
Yeah, so this is why narratively you would pick the projective ideal, is it's always in there. And yeah, so that's why I do it, that's why I like it.
but you don't have any condition.
This is like a little bit like more I would say hand wavy, is I've heard before that if you look at the projectives, that's when the theory acts most like the derived theory. So I've heard from people who are studying derived Skein modules that there's some reason why it's most natural to focus on the projective ideal. But I don't, this is.
No, of course, it's
This
the
is like
fundamental ideal in some sense, but I can construct, for example, three-manifold construction with these guys,
Yeah,
three-manifold environments with, but not with any tensor ideal, for example, with ideal, I mean, like it's like I'm use Skeins.
Yeah.
But not 50, but three-manifold, for example, variants. Skeins, no, but not for a many tensor ideal, it should have a trace, modified trace. And
there's tensor ideals with that one.
It doesn't need a trace.
no, I'm telling you, I'm gonna give you like in some construction, when I use tensor ideals, I require a trace, modified tracer. And we have like nice examples when
Yeah.
I mean you have continuous many, well, like.
I mean, for this
many
construction, I think you don't.
But this kind, you don't need any trace.
You don't need any
This
trace.
would be something that you would get out of this construction,
It-
not like input it into it.
You don't need it, but it could become very stupid because for instance, you could also take all objects, but they also do this co-completion step. So in the co-completion, the objects that were already there before become projective afterwards. So if you already put the unit in,
Yeah.
then in the co-completion, it would become projective. So secretly you would make things semi-simple again by
Yeah.
including all objects. So you can obviously do it, but it would just be not the thing you want. It would be a very.
Yeah, my question, like, for example, if I believe if I put not projective ideal, some other nice tensor ideal, which I mean, I have like many of them, which has nice really trace function with same properties, I like projective. I believe your construction will maybe
Yeah.
pop it up.
Yeah,
But I wonder if you could say any tensor ideal,
So,
which I mean, might be not trace.
so, yeah, it's the generality is that here, you would actually put like a CP ribbon category, so like something that's ribbon except for only the compact projective objects. So it doesn't even need to be, I mean, in the paper and in talks, we want to talk about these tensor ideals, but like you don't need it to be embedded in this larger category for it to make sense. So it's.
Yeah. So you don't ask even sorry, don't ask if you know. Any other questions, comments?
Is it just so the A here? I mean, you basically just said so. This is really just CP written. It would work.
Yeah, so this would be, yeah.
So in particular, you can also so it doesn't have to be finite driven. You can have the infinite examples. It still works.
Yeah.
Okay.
Okay, let's thank Jennifer again. And we have plenty of time for discussions. So we will finally resume after lunch at 2:30 here.
Yes, but okay, remember that there is the canteen.
Or cathedral maybe. Yeah, there's canteen, of course, canteen. I think the tickets
You
will.
need the canteen, so you need the ticket.
It's in the cathedral, or
No.
I think at the cathedral, right?
I think it would be more or less the cathedral. We put the tickets in the cathedral. In any case, if you don't have a ticket, you will look for one of us.
Yeah.
We are not so much today, so.
Yeah. And the afternoon talk will be.
After 4. And after 2.
But in your place in amphitheater.
Yes, today we come back to Amsterdam.
Okay. Nice. Nice. Nice.